Okay, so we're recording. Here we go. Last time we were talking about section 1.6. We actually finished section 1.6. I won't repeat any of that. But moving on now to section 1.1. Remember, we are doing these a little bit out of order. Yeah, there's very little for me to say about section 1.1. I'm pretty sure you all already know all of that stuff. So just a couple of comments. One about notation. You can either use bold or a vector hat to represent that something is a vector instead of a scalar. Suit yourself. I just find that when you're writing by hand, bold is really hard, right? It just seems like I've always felt like when books do that, they're just kind of showing off, you know, that they can do something that we can't very conveniently do with a pen. So I think that's silly. We should have a notation that everybody can use, including people writing with a pen or a pencil. And so I have a preference for the little vector arrow hat notation such as that there. Now, you are welcome to do either one you like. I don't really care. You should also know, now this is just a cultural point, but at a certain, there we go. At a certain point, the higher you go in math, eventually, they stop putting the little hat on there, too, and they'll just write V as just V. That's it. And the idea is that earlier in the paper or the book or what have you, when they defined V, they said V is a vector. And they're like, okay, so we already told you it's a vector, right? And then you have to keep track in your mind. I find that a little, I like the little reminder. So even though I've been to those high levels, I prefer actually still putting the little thing up there. Okay, the other thing is about how to represent this vector here, represented by that arrow. The book sometimes likes to write that as P1, P2, as I have written there. And I guess that's fine, but I'll point out that another way to write it is P2 minus P1. After all, don't forget, P2 being a point is also a vector, and P1 being a point can also be thought of as a vector. And so this green vector, arrow, is literally P2 minus P1. So now take your pick. Case could be made. There is one less pen stroke here, right? And if you're really trying to preserve those pen strokes, then I guess that's an advantage. I'll tell you what I really like about this notation, though. It shows the algebra. Algebra is useful. Algebra is a good thing. If there is an opportunity to use some good thing, I want that to be visible. I like seeing it. Right? So I basically never use this notation other than to say that I never use this notation. And so you'll always see me writing it like that. Again, suit yourself. Not required either way. Okay, any questions about any of this? Very good. All right. Okay, that's section 1.1. There's a bunch of other stuff in 1.1. Y'all can read tough choices. Remember, I only have so much contact time. We're already behind schedule. Anyway, make sure you're good with everything else in 1.1. Okay, 1.2. Again, there's more stuff that y'all, I think, either already know or can easily read yourselves. I am going to spend some time, though, talking about parametrizations. I think this is new to many of you, and I certainly can't assume that you know it. So what is a parametrization? It gives position as a function of, I'm going to say time, but it doesn't have to be time. Technically, a parametrization is position as a function of a single parameter. The thing is, if you think of it as time, if you have position as a function of literally time, that describes a motion. Right? Or if you're talking about a curve in space, it's like you're following how the parametrization is drawing the curve. Where is the pen's position as time passes as you draw that curve? And I find that to be a really useful metaphor and sort of way of visualizing. So I like to think of it as position as a function of time. Okay, quick example. Here you go. position, right, as a function of time. X and Y coordinates, both functions of time. And so this is a parametrization. Now, what is this a parametrization of? What curve is this tracing out? Well, look, you can just remember that X is this function and Y is that function and start plotting points, I suppose. So in particular, you can, let's see, let me come up to here and we'll draw a little XY system. And let's see here, plug in t equals 0, and you get a point, let's say about right there. You get 1, 0. And then as you plug in more and more values of t, increasing, let's say slowly increasing values of t, these points, you can just plot them one at a time, right? And they will kind of go like that. So, yeah, you can kind of just watch it happen in some sense by plugging in different values of t. Everybody good so far? Now, what curve is that? You're going to notice as you plot more and more points, it kind of looks like a circle. How do we know it actually is a circle? Well, you can literally take this formula for x and this formula for y and plug it in and directly confirm that every one of those points satisfies this equation. Now that's just the Pythagorean trig identity. Right? I mean, x is cosine, y is sine. This becomes cosine squared plus sine squared, and that just works. So that means that every point created by this parametrization satisfies this equation, namely is on this circle. And that confirms for us that indeed this traces out actually literally the unit circle. You buy it? Everybody happy? All right. Okay. Moving along. Now here's a different one. Different parametrization. How are we going to understand this parametrization? I'm going to show you 2 different ways to understand this parametrization. By the way, this will often be the case. Math is not just a bunch of algorithms, right? Math is creative use of various tools that you've learned in different contexts. And I'm going to show you 2 different tools for your mental toolbox. 2 different ways to approach this question. And here we go. First one, remember, when you have a parametrization, it is telling you your x and y coordinates as functions of time. Now this is written differently than the previous one, right? I've written it in sort of a ordered pair notation. But don't forget, that's telling you the first coordinate is x. That's the formula for x, and likewise the second one is y. Okay, the trick, the tool that works in this case. Step 1, solve for t in one of those equations. That was easy in this case. Solving for t. Next step, remember that the other equation is a formula for what y is, and you can plug in your newfound formula for t into that second equation for y, which of course turns that t into that x plus 1. So you solve for t in the first equation, plug it into the second equation, and lo and behold, what you've got then is an equation that involves x's and y's. You might say we've eliminated t. And this, of course, is a familiar relationship between x and y. This is the equation of a line. And therefore, now let me clean up my mess. Therefore, this parametric curve is a line. How we doing? Everybody happy? Okay. All right, now, different approach. Same curve, same parametric curve, different way to do it. Reminder, don't forget, the first coordinate is telling you the formula for x. The second coordinate is telling you the formula for y. So take your formula for x and your formula for y and try to figure out what would you have to do to this x formula to turn it into the y formula. You can go the other way if you prefer, doesn't matter. Now in this case, this is pretty tractable because this is a first order polynomial of t. And I'm going to try to turn it into also a first order polynomial of t, right? The algebraic process, how do you get from here to here algebraically doesn't look that scary. And in fact, it's pretty straightforward. You can see what I've done down here. Well, I had to multiply this first formula by 3 and then add 7. That's just me trying to turn this into that. And as such, having done so, notice that then gives me this relationship, otherwise known as that equation that I had found previously with that other method. Everybody on board? Different way to do it. Take your pick. Now, let me rephrase that. I say take your pick. It is not the case that you can just decide which one of these tools you like better and stick with that one always. Right? There are going to be some cases where this method here is unacceptable. There are some cases, for example, in which it's really hard to solve for t. What if, instead of being a nice simple formula, what if this was some sort of weird quintic polynomial? How do you solve for t? Right? On the other hand, sometimes this is bad. If the process of how you would turn the one formula into the other, if these two formulas just look so different, one of them's got cotangents in it, the other one's got exponentials in it, how do you, oh gosh, I don't even know how do you do that, right? So each one of these has its limitations. So again, that's why I emphasize the tools in your toolbox kind of metaphor, because that's how tools work. Hammers are good for certain things. Sometimes they're exactly what you need, sometimes they're just not. Okay. All right, is everybody on board? Yeah. Okay, here's another one. Different circumstance. Here we're in 3 dimensions, you'll notice. We've got 3 different coordinates. We've got x, y, and z. All right. Well, again, this is just another method that works sometimes. I'm going to start by thinking not about the curve itself, but about the projection of my mystery curve into the xy plane. And the projection into the xy plane, of course, is going to be determined by just, well, what are the x and y coordinates doing? Basically, notice this projection says just ignore z, throw away the z coordinate. And so I have. Now, good news. Cosine t, sine t, we recognize. By the way, this kind of thing happens a fair amount in math. It's sometimes you see something and you're like, oh my gosh, yeah, I've seen that before. I know what that is. Right? So, furthermore, by the way, this specific parametrization, cosine comma sine, it comes up a lot. So you definitely want to make sure that you're really familiar with that one. That's right on the tip of your tongue. Whenever you see that, unit circle. Right? So that tells us that whatever is going on with this curve, I still don't know the curve, but I know that its shadow down here in the xy plane is a circle, unit circle. Is that good? Okay. Likewise, let's do the same thing in the z direction. Now, looking only at the z coordinate. Forget x, forget y. Just looking only at the z coordinate. The z coordinate telling us, you could say projection to the z-axis. Let's just think height, right? This formula right here just says, well, that height apparently is increasing with t. And so that means that this parametric curve is moving upward. Right? So now neither one of these observations tells the whole story, but between the two of them, this parametric curve, as this parametric curve traces out, the shadow is doing this, moving around in a circle in the xy plane, and then the height is increasing at a constant rate. And so you put those two things together, all together then, geometric appeal, right? Something whose shadow is going around in circles, but itself is also rising at a constant height rate is a helix or a corkscrew. Yeah. Okay. Everybody follow? This doesn't always work. This works only when the projections are convenient, another tool for your toolbox. All right. Okay. Moving along. You'll notice all of the examples we've talked about so far assume that the parametrization is given. And then the question is, once we have a parametrization, how do we figure out what that curve is? Now we're going to turn it around. Suppose we know something about the curve. We already know the curve in some sense. How do we create the parametrization? Okay. So this process of trying to create a parametrization is called parametrizing the curve. So how do we parametrize a curve? And again, there are many different methods, and I can't give you an exhaustive list, but I'm going to give you a good set of tools for your toolbox. This is my favorite one to start with, what I call the graph parametrization. The graph parametrization works only if your curve is a graph, and I emphasize now this is a specific and particular thing. We will talk more about what graphs are and how to think about them, et cetera, et cetera. But for the moment, let me just say it's where you've got one of the variables as a function of the others. So think back to high school algebra, and you graph a function, for example. So one of the variables is a function of the others. Okay, so here's the trick. If you have a graph, not that you always will, sometimes it won't be a graph, but if you have a graph, let t be your input variable, and everything is just going to work out. It's wonderful how nice this works. If you have a graph, let t be the input variable. And let me show you in action now. Okay, we want to parametrize, let's see here, we want to parametrize this thing right here, y equals x squared. Notice it is a graph because one of the variables is a function of the other. Is that cool? Important requirement. This only works with graphs. According to the instructions here, it says let t be the input variable. Okay, so I guess t is going to be x. I claim we're actually done here, and here's how that works. If t is equal to x, okay, well that gives me the formula for x. X is, by definition of this construction, x is t. We're letting t be the input variable. And then here's the thing. If x is t, then that tells me that y has to be, just looking at this formula, plug in x equals t, and y unavoidably has to be t squared, and we are done. We have ourselves a parametrization, position as a function of t, for that same curve. So it just works. It's kind of awesome. Everybody happy with that? Real clever. All right. Here's another example of that. Now you'll notice in this equation down here, we can't solve for y. Just algebraically, it just doesn't work. Right? You just cannot do it. Importantly up here, notice it didn't say y has to be a function of x. It just says if you have a graph. So if any one of the variables is a function of the other, it doesn't matter which one. Any one of the variables is a function of the other, then you're in business. And in this case, I can absolutely solve for x. Can't solve for y, but I can solve for x. X now is a function of the other. And this is a graph. And so I'm going to follow the rule. We're going to let t be the input variable. The input variable here is y. So I'm letting t be the input variable. T, therefore, is the formula for y. And if y is t, then unavoidably x has to be all of this stuff right there. And again, we win. We have ourselves now a parametrization of that original curve. How are we doing? Anybody happy? All right. Cool. All right, next one. The next one's trickier, but it's a great tool. Vector algebra. Oh, I'm sorry, question, yeah.
Yeah, for the last example,
Yep.
we make y equal t.
Yep.
I thought before x always had equal t.
Well, in that example, just keep in mind what it means to be a graph is that one of the variables is a function of the others. So here I have x being a function of y. That's what I'm interpreting that as. Right? So x is a function of y, so we let t be the input variable, in this case y. Is that satisfying?
Yeah.
Okay.
Thank you.
Yeah, yes?
You just make, in this case, when you parametrize one of them, you just make the other variable the y or the t, and then you
Yes, solve for whichever variable you can.
Yeah.
Or if you can solve for either, then pick, right? But however it is that you know, in any case that you're able to solve for one of the variables in terms of the other, that creates a parametrization. Yep. All right. Okay, so vector algebra. Turns out that sometimes something that's hard to describe, like intractably hard to describe, on its own can be written as a sum of things that are just kind of easy, as it turns out. And this is one of those times. So what we've got here is a wheel, and I like to think of this as a wheel on a bicycle. And I feel like y'all have probably seen, I know I've seen this a million times, if there's a reflector on the wheel, then you imagine as this wheel rotates, as somebody is riding down the street at night and there's street lights, and that reflector catches the street lights, you get to watch that reflector as it goes along the road. And in particular, it makes this weird kind of jumpy, kind of sawtooth kind of a pattern. Does everybody know what I'm talking about? Okay. All right, so that's what we're going to parametrize. We're going to parametrize that wacky curve. If you try to write down an equation for that curve, it's bad. I'm not even sure it's doable. I don't know how to do it, I'll say that. Right? It's pretty hard. But that reflector, if you look at its location at some point as the wheel is rotated a little ways down the road there, it's a sum of the location of the axle and this, what I'm going to call difference vector, this D vector there. And what we're going to find is that the axle is actually really easy to describe. In fact, you can watch the axle itself as the bicycle rolls down the street, and what you'll find is that axle, it's just nice straight line, right? And this little purple vector, the difference vector, well, it's a little harder to watch, but if you keep in mind that we're talking about a vector here and not an arrow, vectors don't have location. Now the arrow is moving as the bicycle rolls down the street. The arrow itself is moving. We're interested in the vector. And the vector is pretty simple to describe. The vector is just kind of going around a circle. And that's going to be pretty easy to describe. There's some details. We'll go through the details in just a moment. But ultimately what we've got here is we've got a hard to describe thing, the reflector, being a sum of the axle and this purple D vector. Okay, one at a time. Let's try to, let's see here, let's try to describe the motion of the axle. There we go. Again, it moves in a straight line like this. You'll notice if the axle is not on the road, the axle sits up above the road because it's in the center of the circle, and if the circle has radius A, then this height is A, and so the y-coordinate of the axle is A. Is that good? Okay, next, let's talk about what is the x-coordinate of the axle. By the way, we have to make a choice here. Before we do any other details, we have to decide what are we going to view as being t. What do I want to be the parameter that everything is described in terms of? My experience has been that when there is a picture like this where there are angles involved and where the angles are going to matter, the angle is actually very often a great choice for parameter. So I'm going to choose here this angle t. What I have labeled as t, I'm going to choose that to be my parameter. Notice that when the wheel starts, we have that angle is 0 because the reflector is straight down. This angle is measured off of straight down, and so over here the angle is just 0. And furthermore, notice as the wheel rolls, this t increases. So this angle that I've chosen measured in that way actually behaves like time. I feel time ought to behave in this circumstance. It starts at 0 and then it goes up. Is everybody okay with that? All right, so that having been chosen, here's the really clever observation. The x-coordinate of the axle can be thought of alternatively as the amount of road that has touched rubber. And now I'm going to make a physical appeal. The amount of road that has touched rubber has to equal to the amount of rubber that has touched road. Now you got to sit there and think about that physically now, right? Ultimately what this is claiming is that the wheel isn't slipping, right? So if it's not slipping, then the amount of rubber, that's what the rubber does. The rubber is kind of tracing out the road in some sense. So these two green and blue distances here have to be equal. Everybody see the sort of the physics of that, sort of the real worldness of that? Okay. All right, well, good deal. Well, this green is actually pretty easy to compute. That green distance, this is an arc of a circle. And high school geometry gives us a formula for the length of an arc of a circle. And it's this formula right here. It's radius times angle. The radius is A, the angle is T. All right? Okay. All right, so we are halfway there. We've got a formula now for our axle. The location of our axle is that. Okay, so now we're going to change our focus. Now we're going to think about this difference vector, this little d thing right here. Keep in mind, vectors don't have location. I can redraw this anywhere I want. I'm going to redraw it in standard position. Life is good. In standard position, it's easier, right? It's easier to deal with. So I want to understand that vector. Now I need to understand that vector as a function of t, unavoidably. The problem is it's a lot easier to understand that vector in terms of this angle, the good old standard angle theta. And d as a function of theta, let's see here. D as a function of theta is easy. Right? Cosines and sines. Right? So unit circle point of view on sine and cosine. So cool, we've got d, but a problem, we have d as a function of the wrong variable. Keep in mind, this relationship, this sine and cosine thing only works when the angle is measured counterclockwise off of the positive part of the x-axis. That's the deal, right? Our angle, what we need to have d written in terms of, is this angle here. Is just a different angle. So if I have the formula in terms of theta and I want the formula in terms of t, I need a relationship between theta and t. And now just another sort of geometric appeal here, but just notice as t gets bigger, theta gets smaller. But at all times, the sum t plus theta is 3 pi over 2. No, it's just right there in the picture. Everybody buy it? So cool, now I have a formula for theta, and I can take this formula for theta, plug that in for where theta is, and simplify the trig, and what comes out is that my purple vector, what I needed is this formula right here, this function of t. Yes?
Where did you get the baseline?
Yeah, so that's just the unit circle sort of point of view on trig. So a lot of people think of sine and cosine in terms of triangles, and this is very limiting because angles can only be, there's a limited range of values for angles of a triangle. Right? So if you reinterpret sine and cosine in terms of the unit circle, and where theta is just an angle that's measured going around the unit circle, then all we have to observe is that this point, this is a distance a away from the origin, and sine and cosine give the position on the unit circle, and you multiply by a to get on this bigger circle. Yeah. Yes.
So in this case, the cosine is the x coordinate of t and sine is the y coordinate.
Yeah. Well, a times.
Yeah. And it's a vector form with the.
I'm sorry, just a little bit louder.
It's in vector form, right?
Yeah. That's right. So this is a standard notation for vectors that, writing it vertically, first coordinate is x. Top coordinate is the first coordinate, bottom coordinate is the second coordinate. Yeah. Yep, yes?
Going back up to the A vector, how did you know how did you pick what to be your x and y?
That's just from the picture. So looking at this picture, if this is my point A, right, then y is that distance.
Okay.
And so that's y. Yeah. Is that okay? Yeah. Cool. Yes.
So you established it that way because you're conceptualizing t as like that. But
Uh-huh.
if you imagine t as x instead, would it be appropriate to say that it would be like t and then a?
Yeah. Let me just say, if you redefine t differently, then I would have to change everything in here, and so that's gonna make it a whole different analysis. But yeah, you always have these choices. You get to decide what you want your parameter to be. If you're creating a parametrization, then you're in charge of choosing what your parameter is. And I think angles are a good choice. If you have an angle and you want to know a distance, that's trig. But if you have a distance and you want to know an angle, that's inverse trig, and I don't like inverse trig if I can avoid it, right? So that's why I chose it as an angle. Does that make sense? Okay. Yeah. Yes.
You define theta as 3 pi over 2 minus t, which makes sense based on the diagram.
Uh-huh.
I'm just wondering if you had defined t to be from the angle between the horizontal and the
Yeah. So I'm there's a bazillion different alternative choices that we can make, and we don't have time to explore all of them. But yeah, it would be different. And again, you get to choose your parameter however you want. There's pros and cons, and yeah, everything would change. Yeah. Okay, but so I want to stick with this setup just because otherwise it'll take forever. Yeah. Is everybody happy with this? Okay. All right. Okay, so now last thing I want to point out, how did I get from here to here? Right? How did I get from this formula in terms of theta, and then I plug in this theta, and all of a sudden I get this different formula in terms of t. And what I did there is I used the angle addition formulas. So cosine of a plus b is a formula, and sine of a plus b is another formula. Now I'm going to point out, I'm aware that y'all know of the existence of these formulas. I'm also aware that most high schools don't require students to know these formulas. And that might even make sense in that context. But it's in a multivariable calculus class, certainly in this multivariable calculus class, these formulas are going to come up a lot, and I need you to know them. So make sure to look these up in your old books or what have you. I'm sure they're all over the internet. Make sure that you know these formulas. The angle addition formulas for sine and cosine. Just sine and cosine. I don't care about tangent or secant, etc. Just sine and cosine. Okay. All right. Okay. How do we parametrize a line? And again, this is one of these situations where, on its own, a point that is kind of tracing out this line, maybe a little bit hard to see how you would get your hands on that. But I think it works out way easier, very conveniently, if you view it in terms of certain givens. So I'm going to assume that we are given a point x naught that is on the line. Given. And I'm going to assume that we have a vector v parallel to the line. And if you don't have them, find them. Okay? So this construction I'm about to show you requires that we have at least one point on the line and at least one vector parallel to the line. Okay, now that said, how would we parametrize? Well, notice that any point on the line is a sum of simpler things. In particular, x naught, which we already have. If that's really simple, we already have it. And then some other vector parallel to the line, which means that it has to be then a multiple of the given vector parallel to the line. So some scalar multiple of v. So every point x on this line, I can write in this, again, in the sum of simpler things. X naught, easy. TV, easy. Right? So breaking it down, again, with vector addition, gives me this formula for position as a function of time as I sort of trace out the line. This then is our parametrization of the line. Does everybody follow that? Another nice trick. By the way, again, comes up a million times. Make sure you're good with this formula. Make sure to remember it. Be on the lookout to recognize it. In fact, if you notice, let's see, where was the... oh, yeah, it was up here. Yeah. This one up here. You can rewrite this in that form. You can rewrite this as... let's see here, negative 1, 4 plus t times 1, 3. So this is your x naught, and this is your v. That just, okay, so third point of view on how to break down this parameterization. Okay. Okay. I think this is the last one, if I remember correctly, that I'm going to show you before we go on to other things. Yeah. So sometimes you'll want to parameterize something, and it won't be exactly something you've parameterized before, but it'll be kind of similar in some ways. And so sometimes you can take a parameterization you already have and just make observations about certain little tweaks that need to happen to it. And then you can, by way of those tweaks, create your new parameterization. So here we go. Let's suppose we want to parameterize this ellipse with that equation, which of course looks something like that. How are we going to parameterize that thing? Okay, well, we've never done this before. This is not something that I can just recall. But notice that ellipses are pretty similar to circles. And in fact, we know two things. We know, for one thing, how to parameterize that unit circle. Again, our old friend, right? We recognize it. Be on the lookout for recognizing when things you've seen before could be useful. And we know that ellipses are literally what you get when you stretch a circle appropriately in different directions. So in this case, I mean, I can see specifically the amount that I need to stretch in the x direction is, well, what is this coordinate of that vertex, which I can literally see right there in the equation for the ellipse. And then likewise, how much do I need to stretch vertically? Well, I can see that by, well, how tall is this ellipse? What is that y vertex? And again, I can see that right there in the equation for the ellipse. So I'm going to need to take my existing parametrization of cosines and sines. I'm going to need to stretch by a factor of 3 in the x direction. No problem. You want to stretch by a factor of 3? You want to sort of stretch it out like this horizontally? All the x coordinates are going to get 3 times as big. Boom. I just made the x coordinates 3 times as big. Right? Likewise, I'm going to need to stretch vertically by a factor of 2. Okay, cool. Easy to multiply all the y coordinates by 2. Bam. And so, altogether, we have done this deformation. We have deformed our circle that we knew how to parametrize and turned that into now a new parametrization of this ellipse that I needed to parametrize. Yeah?
Is t theta, or is it just...
Yeah, here I'm using t as theta. Yeah, that's right. And this is another, you always have choices as to how you choose your parameters. Here I called it t, but you're right, it is also theta, so take your pick. Yep. All right. Okay. All right, so now there are some misunderstandings about the differences between parametrizations and equations. I think this is an important distinction. Related to this, lingo, terminology can very often create confusion. And along these lines, to my frustration, another name for a parametrization, sometimes they'll call it parametric equations. Well, this is very frustrating to me. Parametrizations and equations, as we're about to discuss, are pretty different things. Structurally, like how they work, how they relate to the curve in question, very different. So to me, when you have different but related things, it's very important that the language keep them separate so that you can unambiguously talk about the relationships between them. And so I think it's just terrible to call this a parametric equation. But it's out there. Be aware of it. It's another one of these things that you'll never catch me doing, other than to say that you'll never catch me doing it. So a parametrization. What is a parametrization? What it does is it is a point generator. A parametrization creates points on your curve. It's a point generator, pretty literally. Now, very importantly, that's not what an equation is. Equations don't generate points. That's just not how they're built, right? You can't take an equation and just kind of turn the crank and out comes a point. That's not what it does. An equation is a point tester. If you come to me with a point and say, hey, is this point on the curve? An equation is something that I plug into, and either the equation works or it doesn't. If the equation works, then yes, it's on the curve. If the equation doesn't work, then no, it's not on the curve. It doesn't satisfy the equation. So does everybody see the difference here? So generating points and testing points are very different ways to kind of go about describing a curve. Yeah? All right, so I think it's important to keep these in mind, and it is particularly helpful for this next example. So here's a parametric curve, and by the way, we haven't seen this just yet, but we will very soon. This is the equation of a plane. For the moment, don't worry about that. This is the equation of some geometric object. We don't really need to know what it is. But I've got a parametric curve, and I've got this geometric object here, and the question says, what points do these intersect? What points are on the parametric curve and are also on this other geometric object? Again, turns out it's going to be a plane. So the big idea is to just keep in mind what these do. This parametrization generates points, and those generated points, here they are. When you generate a point, that is telling you the x, y, and the z. We can then test, in this sense, those generated points. We can take these x, y, and z, ask if they satisfy this equation by plugging them in and seeing if the equation works. So we're literally going to test the generated points. And again, the foot in the door, the thing that makes you think of this is to have a good, clear understanding of what these things fundamentally are. That one of them generates points and the other tests points. And then the Legos just kind of fit together. Points come out of the one, they go in to the other. So all together, the whole process, you can just solve for t. And t equals plus or minus 1 is what makes this work. That means these are the values of t that we're interested in. But do keep in mind what the question asked. The question asked for what are the points. The question didn't ask what values of t. The question says what are the points. Okay, well, we've got the t's. We want the points. And how do I turn t into points? Well, I plug into the parametrization. And so, you got to do the arithmetic there, and that will tell you those 2 points in question. Is everybody on board? Does everybody follow all that? Cool. All right. So some of you may have seen this. This kind of thing I kind of feel like should have been in a linear algebra class, but I accept that I guess it isn't, at least not for all sections. This thing called symmetric equations of a line. This is the answer to a question that we haven't really thought of yet. We've talked about how to parametrize a line in R3. Right? It's x naught plus tv. We have this formula for how to parametrize. That's a point generator for the line. What if I want a point tester? How would I test? What would that test look like if this is the point generator? So now I'm going to start off by giving you a kind of a bad answer. One way to test a point is to ask, well, does there exist some value of t for which the point generator generates that point that you're interested in testing, right? I mean, it's a silly way to say it. It's also kind of useless. I need to know if a t exists that generates this specific point, x, y, z. What am I going to do? Just keep picking random values of t and tossing them in there and just cranking out point after point and fingers crossed, I hope I get lucky and accidentally generate exactly the point that I'm looking for. It's impractical, right? That's not a good approach. Okay. So what turns this into a good approach is to realize that I can take this vector equation here, this parametrization, and I can solve for t. In fact, I can solve for t 3 different times. This t, just by looking at the x-coordinates, must be that. Just by looking at the y-coordinates, must be that. And just by looking at the z-coordinates, must be that. So now let's re-evaluate now our kind of ridiculous and impractical point tester. Is there a value of t that makes this parametrization generate my particular point? That I don't know, but now new question. Is there a value of t that equals that expression, and furthermore also equals that expression, and furthermore also equals that expression? Is there a value of t, let's say, that simultaneously equals all three of these things? Now let's take a quick pause. How could t, it's got to be the same t, how could t equal to all three of these things? Can t simultaneously equal to 4 and 7 and 10? No. No way. It's ridiculous. Can t simultaneously equal to 4 and 4 and 4? Yeah. T can be equal to 4 and 4 and 4 by being 4. Right? It's silly, right? It's one of these things that's the hardest thing about this point is how painfully obvious it is. Does that make sense? So, okay, so the answer is yes. There is such a t if and only if these three things are all equal to each other. And this is our point tester. This is something you can just plug in. You take your, whatever the XYZ is that you're interested in, you plug in the XYZ, you compute these three things. If they're all the same, that's on your line. If any one of them is different from any of the others, then no, then nonsense. It just doesn't work. So there's your point tester. This is called the symmetric equations for a line. And nice construction. Sometimes you have a point generator, but you want a point tester, and this is how you do it. Okay. All right, let's see here. I think I'm out of time. Let me make a real quick reference to, you know what? Now this is a good stopping point. We'll draw the line right there. Okay, see y'all later. Have a good rest of your Wednesday. See you on Friday.